Thank you, Tony. Thank you, everyone, for coming, and thank you for inviting me. So today I'll be talking about a result on almost linear time algorithms for Maxwell, min-cut, and several other problems. This is a paper set to appear at Fox, and this is joint work with several amazing co-authors: Lee, Rasmus, Yang, Richard, and Max. You see, this is clearly a COVID generation result, right? Like we are all spread over different institutes. Okay, so excellent. I have plenty of time. Please stop me to ask questions. I expect basically everything, like you should be able to follow everything. Ask me a question if something's not clear. So max flow, right? It's a problem all of us have seen in our algorithms course. It's been studied for 70 years, right? Like here's a picture from a 1952 paper by Harris and Ross, sort of trying to identify the capacity of the Soviet and Eastern European rail network. So it's not only was defined a long time ago, it's been very intensely studied. You might ask why. One big reason is that it's a very powerful primitive. Many problems that you could try to identify can be reduced to maximum flow and or min cost, as we will deal with. And the other challenge has been that it's been a formidable opponent, and a lot of techniques and a lot of have been developed to try to speed up algorithms for max flow. But let's say like this. So until a couple of years ago, the best running time was still m to the 1.5 in Sparse class. Even though it's so well studied. Good. So let's just formalize the problem so that all of us are on the same page. We work with directed graphs. So every edge has a direction. We'll use the standard notation that the graph has m edges, n vertices. And let's just pretend two special, a source and a sink. Every edge has a capacity, UE. Well, we'll assume that this capacity is integral between 0 and capital U. And so I can give you explicit dependencies on U, but for simplicity, I'll just assume that U's are bounded by a polynomial in your parameters. Right? So here's an example graph. These numbers are capacities, you have a source and a sink. And what's our goal? Our goal is to route maximum flow from the source S to the sink T, subject to your direction, right? Flow on an edge can only move along the direction, and it has to be bounded by the capacity of that edge. So on this edge, you can only have flow going from left to right, bounded by 1, right?
And you also need conservation at every node.
You need conservation, right? So at every node, but except for the source and the sink. So good. So let's just formulate that. So the classic view of flows has been it's a collection of flow paths, right? You identify paths from the source to the sink, and then send some flow along these. Right? That's the classic combinatorial view. Here's one path. I'll send 1 unit of flow along this. Here's another path, 1 unit along this. Here's one more. I'll send 1, and here's one more. I'll send 2. Right? That's a classic combinatorial view, prevalent for significant chunk of the time that Maxwell studies. We'll take a slightly different view, the linear algebraic view of Maxwell. So think of flows as just a vector assigning real numbers to each of the edges. Right? So I took the same flow and that converted that to just these purple numbers on each of these edges. But of course, every such vector is not a flow. So what do we want? What are the constraints we need for the flow, for this vector to be a flow? The easy one is that it must satisfy your direction and capacities. So Fe is non-negative and bounded by the capacity on every edge. Right, that's the easiest one. The more interesting one is the conservation that was pointed out. Let me make that conservation a little simpler. Let's add this. So this was our original graph. I added a special edge from the sink back to the source. Okay. And what I'll do is along this edge, I will route everything that comes into the sink. So the sink is getting one 3, right? 5 units. You route 5 units back on this edge, back to the source, right? Now the conservation is very easy to state. Now I want that at every single vertex, including the source and the sink, inflow equals outflow, right? So these are linear, it's a linear equality at each of the vertices. You look at the flow incoming, that's 1 and 2, that's equal to the outgoing flow here, 3. Right? All of us with me? Great. So now our goal is easy, just route the maximum flow on the single edge, E sharp. Right? Like on the single edge. So I can capture this using a linear program, right? This is one of the most easiest examples of a linear program. So now you want a vector Fe that's bounded between 0 and the capacities on each of the edge. So you have a constraint for each edge. For every vertex, you have an equality flow constraint, right? The flow conservation constraint, and your goal is to minimize. So I wrote max Fe as min minus Fe. You will just see in a second why. So good. So this captures linear max flow. This is a linear program capturing max flow. And in terms of this problem, our result is that we can solve this linear program exactly in almost linear time. Right? So for those who might not be familiar with what is almost linear time, this is almost linear time. N to the 1 plus something that vanishes as your parameters go to infinity. So think of it as like 1.1 plus epsilon, and you can take epsilon as small a constant as you want. Right? That's and
how good is your little of 1?
Sorry?
How good is your little of 1?
It's log n to the so let me write it as m times something, and that factor is 2 to the log n to the 7/8. Okay, so ugly enough that I don't want to spell it out.
Sure, I just was curious. Thanks.
Thank you. Okay, good. So this is the classic max flow, but actually we can solve very general problems. And I wrote the max flow as this linear program just to tell you what is a general problem we can solve. You can replace the cost. So previously our cost was just maximize the flow on a single edge. Now you can replace this cost as minimizing any convex cost of the flow that's separable on the edges. So you have a sum over edges, a convex function of the flow on the edge. And this function can be different for different edges. Right? And you still have your direction constraints, capacity constraints, and demand net flow constraints. And we can solve this problem to very high accuracy in almost linear time. Right?
I'm not sure I understand what it means.
Okay.
Convex.
Good. So these two are fine, right? We're still looking for a flow, satisfying your demands and satisfying your capacities. Now the cost can, so previously the cost was just one edge. Min cost flow would have cost as a linear function of the flow. I'm saying now you can even have a convex function where, so each of these is a convex function. So let's say, for example, you can think of Fe to the 100, right? So it can solve P norm flows, or you can have entropy of F, so minus Fe log Fe, again a convex function.
It's a linear combination of convex.
So that's right. It has to be separable over edges. That's important.
What does that
Like I can't allow a convex function to involve F1 and F2, right? Like there's one convex function of F1, there's a second convex function of F2. So this separability is important, but once you have this separability, we can solve the problem. Right? Great. So this is very powerful. We can now basically solve a host of well-studied problems in almost linear time. So immediately you get bipartite matching, min cost bipartite matching, min cost flow, negative edge shortest paths, worker assignment, I guess that's bipartite matching, optimal transport, right? Like a discrete optimal transport, directed flows with vertex capacities, they are reducible to these undirected vertex connectivity, flow diffusion. So these, in fact, all of these can be reduced to min cost flow. You only need a linear function, but non-linear gets us even more power. We can now solve matrix scaling, almost linear time. We can solve isotonic regression. So
what's on the right? What's the difference in the right and the left?
good. So the left ones only need a linear cost function.
Oh,
But because we can do convex, we get even more, right? Like all of these reduce to min cost flow. We can get P-norm flows like, right, Fe to the 100 or entropy-regularized optimal transport, which turns out to be the dual of matrix scaling, if you're familiar with those. Right, so a lot of these problems now just fit in this framework and you get almost linear times. Yes?
Can you do like the lowest theta function?
No, because that has an STP constraint, right? It has a positive semi-definite constraint. So we have the flow constraint. You have to have a flow and then non-negative cost functions, and this cannot capture a PST constraint. More questions? Okay, so in the rest of my talk, my goal is to give you some of the key ideas that we introduce and how they are different from the previous results. My hope is you'll at least take away, a high-level view of how does the algorithm work, what are the key innovations, right? But yeah, any questions I can. Okay, good. So before we dive into some more results, for those of you who might be somewhat familiar with the fact there's been a lot of work, I'll just try to highlight just a little bit, in an impressionistic way, how are we different? What were the obstacles that we needed to overcome, and why is our work different from the previous results? So as I said, so here here's a timeline going back to the 1960s, starting from Ford-Fulkerson, right? One of the first algorithms that actually gave some running time bound for small capacities, all the way up to Goldberg-Rao, which is 98, right? So this is almost 50 years of work. The view of flows was completely combinatorial, right? Like collections of paths, you're sending flows and paths, or blocking flows. And I want to separate this as that they were thinking of, like, you can think of most Maxwell algorithms as an outer algorithm and an inner algorithm. Okay, what do I mean? Let me explain. So all of you are familiar with Ford-Fulkerson augmenting paths, right? Find a path, send some flow, construct a residual graph, find a path, send some flow. So there, the inner algorithm, what I'm calling the inner algorithm, is just, I give you a path, you send some flow in it. There's an outer algorithm that, given a flow, finds a residual graph, and now you find again a path to send flow, right? So there's this back and forth, and I mean, for Ford-Fulkerson, there's not that clear a distinction, but the more you get into the algorithms, there's clearer distinctions. Like, if you've heard of the idea of blocking flows is the inner algorithm, and there's a way to construct the residual graph again outside as the outer. So all of these works were working with combinatorial inner and outer structure. Right? This changed in 2008. Work of Deitch and Spielman actually posited that we could do as good, if not better, by picking a more numerical outer algorithm. So remember, we're working with a linear program, it's convex programming. So they said that you could pick interior point methods, which is a particular nice way of solving convex programs, but in particular linear programs, as your outer algorithm. That gives you an inner algorithm that's now still like, it doesn't have an easy combinatorial interpretation, but it has a more numerical optimization perspective. So you get this separation. So Deitch and Spielman sort of said both a numerical outer algorithm and a numerical inner algorithm could still already match the state of the art, where the outer was essentially black box, interior point methods that was known from convex optimization. The inner turned out to be L2 norm flows, which is the famous work of Spielman and Teng, if you've heard of that. So combining them, they matched the state of the art. Since then, like this really sparked a new era of algorithms in Maxwell. There's been a lot of work, but most of them are focusing on improving this outer numerical interior point method. Okay, so all of these works, they get improved running time bounds, but they're focusing on improving this iterations of the outer algorithm. So, but it might be useful to say one more thing. So here, thinking of Dicey-Spielman, they said IPM black box. They tell you that you solve to solve such a linear program, you get square root of m outer iterations, right? So square root of m outer iterations, and then they were able to solve the inner problem in almost linear time. So then you get an m to the 1.5 root m outer iteration. Then you get a graph and a problem, an inner problem. You solve that in linear time, you get m to the 1.5. And the focus of all of these works was to improve the outer iteration, right? Madhuri's famous result that first made a breakthrough over m to the 1.5 was pushing this down to 3/7 outer iterations and then so on. Lee Silver did root n, then we got 1/3 and so on. Right, so the focus was outer. The inner, for each of these problems, the inner problem was still linear, right? It took linear time at every inner iteration.
So what about the last work of Brand et al.?
Good. So this one, that's I'm coming to. This one is a little more interesting. It's linear, but they are able to be linear in n by making some interesting, like because the problems are not independent, one iteration per other, it's linear in n. So you get n, and so they combine this Lee Silver root n IPM, and you get an n inside, so you get an n to the 3/2 rather than an m to the 3/2. So, but they do require some kind of dynamic algorithms trying to identify how problems change one to the other. That's right. So it's only very recent, right? So this is just 2 years ago. And then this last one, which is the first algorithm to shave 3/2 for large capacities. Gao, Liu, and Peng, and then Brand et al., like I just combined them to give us. They started identifying that maybe we should try to make the inner problems faster. These inner problems are not independent. You get a sequence of them. You can relate one to the other. Oh, you are changing a little by little. Maybe we can maintain the solutions. Great idea, but the improvement was just headline, right? This is 1.48. Okay, so if that made sense, I can try to tell you how does our work contrast. So we achieve almost linear time. Our work is an interesting contrast. So we pick an iteration in IPM, but unlike all of these works that pick the root m or better iteration items, fewer outer iterations, we go worse. We pick a slower IPM, almost linear number of iterations. But at the cost of picking a slower IPM, what we get is a combinatorial inner problem. Something we can deal with graphs, paths, cycles, trees, and much more easily. And we show that on an amortized sense, right, like all of these problems together, each of them only needs like about a constant time rather than linear time. Much, much faster, right? So we can maintain these solutions for these iterations really quickly, and that combines together to give you almost.
So is the space the big difference in the space for yours versus the previous one?
No. Yeah. All of them keep basically almost linear space.
There's no dependence on U at all?
Good. I'm hiding dependencies on U.
This assumption.
So, but it's polylog, it's log squared U. It's log squared U. So it's not poly in U. So the poly in U dependencies I've explicitly shown because that means you can't work with large capacities. But we get poly log U, so that's okay for. Okay, so that's really a bird's eye view of like a stylistic view of how do we contrast. So now let me dive in and start showing you the key ideas. Okay, beautiful. So first, the first piece that we talk about is that we introduce is this slower interior point method, which we call the L1 IPM. And this is our outer algorithm in the problem. So let's go back to the linear program. You can visualize linear program, right? Like I don't know how to draw a three-dimensional picture. So let's say it's a 2D linear program. These are our facets, each of these given by our inequalities. And you have a cost function, linear, let's say, a linear cost function that you are minimizing. So if you've seen simplex, if you've seen these algorithms, all of them try to basically stick to these facets, move from one corner to the other and improve, right? Interior point methods take essentially a completely different view. They will walk strictly in the interior of the polygon, okay? And the one we'll work with is a potential reduction interior point method inspired by Karmarkar. Like this one is exactly Karmarkar. So Karmarkar said, let me define a potential function in the interior of the space. It consists of two terms. Okay, let's parse this slowly. So the first term is a log of the cost minus the optimal. The optimal you can guess by binary search. Suppose it's given to you. Right? The log of the current cost minus the optimal. So it introduces a strong negative gradient in the direction of optimality, right? So it forces you to improve objective if you were to reduce this potential function. And there's a second potential function, one corresponding to every edge, that is log of the flow plus log of the capacity minus the current flow. And it's with a negative sign. So as you get close to either zero or saturating the capacity, it blows up. It gives you a very large contribution to the potential. So the second term keeps you far from each of the hard constraints. Right? And you
In the middle.
so
You're trying to stay in the middle.
yes, you're trying to say sort of equally far from all of your constraints and still make progress in the objective.
So what exactly are you doing with the optimal function? You can do binary search, sure.
Yeah, so this is just a scalar. Let's say binary, you do a binary search and somebody's given you what is your guess on the
So
optimal.
there you're sure, but then that makes it approximate.
But it's a log accuracy, right? Like I can get a 1 + 1 by poly accurate.
Okay, sure.
And for max flow, once you're that accurate, you can just round it off. So we'll know what.
Sure. Yeah.
No, good questions, please. Any more questions on the IPM approach? So I mean, I'll going to show you more. So you put these together, you get this convex functions. I've tried to, like, this is really, I wrote code, and this is these are equilevel sets of the gradient functions. So you can see there is this boundary that's keeping you away from each of the constraints, but in the direction of the objective, you get a sharp descent, right? So what is the idea? The idea in IPM now, the intuitive idea is just clear. You manage to start from somewhere that's somewhere roughly in the interior, and you keep taking steps that improve your object. Right? This potential function is not convex, right? Just to stress this, it's a difference of two convex terms. It's not convex, right? If it was convex, things would be easier. But it's not convex, but you can still make progress on it via gradient descent, right? Like if you've seen an idea of a gradient descent, you can make progress and definitely get to the end. Right. So you start from somewhere, F0, make progress, like just keep taking small steps that improve your objective. And then finally, when you get very close to the, like in terms of optimal objective value, then by integrality, we are able to just go stick to a vertex and round it. Right? That will give you the optimal solution. Right? Okay, so this is a sketch. How do you execute this? I give you a step. How do you actually find a good direction to make progress? Okay, so I'm at F, let's say. That's my current flow, current feasible flow. I want to move to F plus delta, add delta. Okay? This delta must be a circulation. It should not change your demands, right? The net, right? So F has the same demand, net demand as F plus delta, so delta is not changing. It's a circulation. Okay, so Karmarkar proposed the following strategy. He said, you take your potential function. So phi is my potential function.
Sorry, what do you mean by circulation there? I think I didn't. get
Good. So thank you. So by circulation, let me make this good. This combination is interesting. So it means that V transpose delta is 0. Right. So delta is such that every vertex has inflow equals outflow. So this means, this implies that V transpose F plus delta must be equal to V transpose F. So the demands remain unchanged if I add delta. The vertex demands, the net vertex demands.
So there are two types of hard constraints. One of them you're going to put in the potential, the other you're just going to enforce.
But so the equalities we will keep, like we will always stay exactly equal. The inequalities we convert. The inequalities are always like this, morally always thought of as the harder constraints, and we convert them to soft potential functions. Good. Thank you. Right. Okay. Good.
I didn't get like
Yeah.
every time you make a local change and impose the function, so then you get a local maximum. So how do you get like an actual maximum?
Local. We are looking for minima.
Minimum. Okay. Sure.
Okay. So we are trying to reduce the function. So this function is a strict difference of two convex functions, right? So you don't see any valleys, like it really looks like a smooth, like towards the edges it looks like this valley, and then this valley is gradually sloping downwards in the direction of the objective. So it's a very simple non-convex function. Right, you can like numerically, algebraically, you can very easily prove. Let me show you. Okay, let me maybe just give you the proof. So here's your objective function, right? Let's say this objective function is really large and negative. Okay, the key observation is that this contribution is bounded above. So minus, like this is a function like this, right? Like log fe plus minus log f. No, sorry, bounded. Like this term cannot give you something that's very large and negative. Sorry, it's bounded below. It's a convex function. It's bounded below. Then if the entire sum is really large and negative, most of the contribution is coming from here. And that tells you that C transpose F is close to the optimum.
I guess a priori you could still get stuck in a local minimum that is far away from the corner, or not?
No,
you can't.
No, right. Let's just take a. So okay. So just consider one edge, right? Log f plus log. Let's say capacity is 1 and 1 minus f. That's minimized at half. So that's 2 log half. That's it. You cannot be any. This term cannot be any more negative than that. So if my sum is much smaller than m times 2 log half, then the first term must be large and negative.
Right. So after some time, you know that you will not
That's
stuck. But if you start from a very bad point, a priori.
Good. So we have to prove that you will be able to make progress locally. Right. And that's what we'll argue. Thank you. So you do have to prove that if I'm starting at any f, I can find a nice delta cheaply that will make progress. Good, right? So that's the obstacle. So Karnakar gave the following recipe. So take your potential, write a second order Taylor expansion. Right? So you get your constant term, phi of f, a gradient term. G is my gradient of the potential, gradient times the step you're taking delta, plus a second order Hessian term. I'm writing it in a way that's somewhat convenient to me. So this is like if the standard Taylor expansion series would give you delta transpose H delta, right? Half of delta transpose H delta. And then rewriting it. So the Hessian here is diagonal, right? Like because my convex function, the potential just has these log fe log u minus. Ignore the Hessian of the first term. We'll just forget about it. So think of the Hessian of the second term. the Hessian is diagonal, right? 1 by FE squared plus 1 by UE minus FE squared, right? So that square term, I take the square root of those squares and roughly write this L, which is 1 by the smaller of FE and UE minus FE. So up to some constants, I'm writing this Taylor expansion. So I approximated the Hessian up to a factor of 2, and you can, the quadratic term can be written as the following. So let's interpret what is this. So FE is your current flow. UE minus FE is the remaining residual capacity in this edge. You take the smaller of these two and invert it. Why am I doing this? So the smaller of these two tells you how much flow can I move by without violating either of the two constraints, right? I can either remove FE, that hits the first constraint, or I can add UE minus FE, that hits the capacity constraint. Take the smaller of the two. That defines my validity, right? Like if I move within this, then I won't violate any of the constraints. And if I use that to scale delta on that coordinate, right? I penalize the step on that edge with the inverse of the residual capacity.
So is it like changing flow by minus FE to plus UE minus FE?
It's not changing it, but so you got these two constraints, right? Like two limits. You take the smaller of the two, and sort of I'm softly penalizing it by like if your residual capacity is small, this term is larger, going by the inverse. Right? If my residual capacity is 0.1, then this length is 10. So I penalize a step on that edge much more.
So I'm just confused because what if your residual capacity is large but your flow is small? Even then, why are you penalizing it? I'm confused.
Because if the flow is small, so let's say if flow is 0.1, I can't subtract more than 0.1 amount of flow, right? This is a symmetric constraint that adding and subtracting, I'm penalizing in the same way, right? So I can't subtract more than 0.1 amount of flow. So I have to take the minimum of the two sides. Right? Good. And the symmetry is actually very important because it's what does this Taylor expansion and the potential function and the Taylor expansion done? At this point, I don't have to care about the hard constraints, right? You really just think of, like, we will argue that you maintain feasibility. Other than that, to you, it's just a convex function defined everywhere that I'm trying to minimize. So you never get very close to the hard constraints. Right? That's the magic of IPMs. Right, so write this Taylor expansion. This Hessian is diagonal, right? And just minimize your Taylor expansion. So you minimize it over circulations, right? You're trying to add a circulation. You find a circulation that minimizes this quadratic function. This gives you, this was the Daikin-Friedman approach. This immediately gives you electrical flows, like flows that minimize L2 norms, penalize L2 norms, right? So what is this? I'm finding a circulation. I'm looking to minimize the ratio of the gradient contribution, the linear contribution of the gradient and the step over the L2 norm of L delta. This is equivalent to computing electrical flows in the graph. Okay, with resistances given by 1 over LE squared.
Is it easy to see why minimizing this is same as minimizing that? So we want to minimize like this, this the expression you want to minimize. Right. So why is that equivalent to that?
So the easiest way is if I give you let's say So so just writing down the grid, I guess what you could do is like if you just differentiate this, you get that gives you an explicit solution, right?
Aren't they both just linear in delta?
Sorry.
No, they are not. Okay.
No, there are constraints on delta. Like
So you want to just minimize G transpose.
right, so you can write the solution for both of them, and they're basically the same. That's one way to do it.
Ah,
Up to a scaling. This basically takes care of the okay. So you minimize this, you'll get a Lagrange you'll get a Lagrange factor because it's a you'll get 1 over norm and then the L square delta square. Let's just do it. Basically, the two solutions. That's the easiest way to write it. The two solutions are the same. Let's do the first one. So the easy one is G transpose delta plus L delta square. If you differentiate this, then you get G plus L square delta. Right, and this is still subject to your linear constraints, right? And you do this one, you get G minus 1 by times L square delta. So this is the vector, this is a scalar upon delta 2. Right? So up to these hidden scalars, you basically get the same. I guess I messed up, like I flipped the sign somewhere. But you get G and L square delta and G and L square delta. These are all scalars. The scalars are sphere. The direction is the same, and then you can match the scalars. Right, but I've changed some signs. Like,
sorry.
right. So Dyson-Spearman took not the Karmarkar's IPM, a better IPM, but then plugged in electrical flows. They got him to the 1.5. So our first key observation. Okay, sorry. Let me just visualize this, just so that all of us are safe. And then I'll tell you how to do it.
That's easy to minimize.
Yes, so this is easy in the sense that this was the work of Spearman and Tech. 2004, right? Like really revolutionary in some sense, but that was known by that time that you can solve them and you can just plug that into IPM.
And what's the time it takes to do that?
Almost linear, like M polylog. Right. So this Karmarkar IPM has M iterations that would give you M squared, but there's a better IPM that gives the same sub problem that would give you M to the 1.5. Yes.
I'm confused about two things, and probably the answer for both of them will solve each other. But first of all, I understand why morally this penalization function keeps you away from the hard constraints, but it's still not clear that the solution to this would not be outside of them.
It blows up at the boundary to infinity. So the solution, the solution to minimizing this quadratic extension, yes, you have to prove that you're not going too far. That's very good. It's not immediate, like it's not immediate that it's inside.
Like, what would happen if there were?
One sec, let me just take a square.
The second thing, and maybe it's again, maybe it will also answer the first question. It looks like the electrical flow thing is invariant to multiplying delta by a scalar. And
yes,
the thing you're trying to optimize on the right isn't.
Good. So good. So both of these are in fact linked. You have to choose a small step size, and you can show there is a good range. It's large enough that you make good progress, but it doesn't throw you out. You do have to
But then how come it is equivalent if one of them depends on the.
It's equivalent. You can use one to solve the other.
Yeah, it's just a scale. It's just how much do you move along that direction? These scalars, I sort of forgot. I sort of ignored the scalars. So it gives you the same direction, but you have to figure out how far.
Solve the electrical flow to get the direction, and then
That's
to
right.
optimize that thing.
You scale it. You move along that direction to some limited amount that keeps you inside.
Okay, so it answers both.
Yes, here.
So I guess this is just with the setup itself. So if you have multiple optima, is it like?
That's okay. Good. So multiple optima of the linear program.
Yeah.
That actually, this function has a unique
Uh-huh.
point that it will converge.
Okay, I guess, and then this algorithm. So
Yeah. So and these are like if you really do have two vertices, then it will converge somewhere on the face. Neither of the vertices, somewhere in the middle of the face. Okay. So let's just visualize what this is doing. This is not the most natural way of writing electric flows. I wrote it for a reason, so that it'll be easier for me to explain what we are doing. But you can think of minimizing a quadratic expansion. So here's what this step is doing. You're at F, you want to go to F plus delta. At F, you draw an ellipsoid. Okay. The axes of the ellipsoid are determined by these lengths, inverses of residual capacities. Right? So if the residual capacity is small, the ellipsoid is flat in that direction. Right? So it keeps you away from the boundary. In this, you have the gradient gives you a direction. You minimize the gradient subject to being inside this ellipsoid. These are all equivalent up to scalar. It's not exactly, but it's equivalent to a scalar. And that gives you the next point, which is the boundary of this ellipsoid that you move, F plus delta. So there's a question?
You claim that the potential is smaller.
You have to claim two things. The potential is significantly smaller. You are making non-trivial progress, and you don't go outside, right? Like there's sort of there's a good medium that you can make a large step that doesn't go outside. Okay, so how do we change it? Right? Like given this picture, let me tell you how do we change it. We do what we call an L1 IPM. We sloppily upper bound what was an L2 norm squared with an L1 norm squared. Right? This could be much worse by a factor of m, right? But it's a strict upper bound. And we'll minimize this upper bound. Okay. So that gives you a sub-problem. So like visually, here's what it does. Instead of taking the ellipsoid, you embed an L1 ball inside this ellipsoid, and you move to the vertex that minimizes the gradient progress subject to being in this L1 ball.
Reason why, like initial intuition why you made this switch?
Why does L1 work? Yeah, very quickly, but just give me a couple of slides. You'll see why is it.
Oh, this is much easier. I don't know what it.
On graphs, L1 problems are much easier. Like that's the one I would say. But we'll just explore the structure a little. Is the change clear, right? Like from measuring the L2 norm in terms of these inverse residual capacities, we are measuring the L1 norms. So that gives us the sub-problem as a mean ratio cycle problem, which is over circulations, minimize the ratio of the gradient term divided by the L1 length of the cycle. Okay, so previously we had the L2 length, that was electrical flows. Now you have the L1 length. Okay, so let's explore what is this sub-problem. So here's the sample graph. In red are my inverse residual capacities lengths. Okay, and along the directions in black here are gradients. So G, so remember G also has to be specified with a direction, right? So along this direction, G is +1. Right? That's G is the gradient term of the potential. So what does this problem represent? So let's just take a simple cycle along these 4 edges, and send a unit like flow of 1 unit. What is its length? That's easy. The length is 2 plus 1 plus 2 plus 1, that's 6. The interesting term is this contribution of the gradient term. So the gradient term, look at this, on this edge, the flow is opposite to the gradient. So 1 unit, that contribution becomes -4. On this edge, the contribution is opposite to the gradient, the contribution becomes minus of -1 plus 1. That's +1. This one again against the gradient, you get +3. This one is with the gradient, you get +1. So the sum is 1. Right? And if you take the same cycle but flip the direction of the circulation, you get the same length, but the gradient flips side. Right? All of the edges flip side. Right? So in that sense, this is a problem that's intermediate between undirected graphs and directed graphs. You have signs incorporated into the gradients. However, every edge can be traversed in either direction. Just that the sign of the gradient contribution will change depending on the direction you traverse it. Right? And importantly, there are no hard constraints. There's a soft notion of directionality given by the contribution sign, but there's no hard notion of direction. Every edge can be traversed freely in either direction. Right? So edges and lengths are undirected, but the gradients are signed according to direction. Okay, so what is the advantage of moving to L1? Here's, for example, a very simple observation. Now your optimal solution to this problem can be assumed to be a simple cycle in the graph by linearity. Right? This was just not true for electrical flow. Electrical flows, you'll have a flow on every edge. It's a pretty yes, you can describe it by voltages, but it's a pretty complicated description, right? Now it's a simple cycle in the graph. So combinatorially, like if you want to think of it, it's a big advantage.
Can you explain why it's a simple cycle?
So everything in this circulation space is a linear combination of cycles, right? And so the numerator then just splits linearly because it's a linear function. The length, if you take a non-trivial linear combination, it only becomes larger. So one of those cycles in the convex combinations will actually achieve a better ratio or equally good if that was the best. Right? Are we all clear on the subproblem?
What changes in the graph when you change the delta?
When we change, good. So so all of those. So the first thing, like both the things change technically, right? Once you move from f to f plus delta, I have to recompute the gradient and recompute the lengths, right? But they only change on the edges that you're traversing, right? So at least some notion of stability is sort of clear that you only have to change them on the edges that you're routing. Okay, so here's a theorem for this L1 IPM. So there's an IPM for max flow, but or min cost flow such that you only need almost linear number of iterations. So now it's more than before, right? There are IPMs with root m iterations, and people are focusing on improving it. Now it's more, but it's still just almost linear. At each iteration, the subproblem is a min ratio cycle. Right, this L1 cycle problem. 2, you don't have to solve these problems exactly. You solve them crudely, like a subpolynomial ratio, subpolynomial approximation factor. That's good enough. We'll just pay this factor in the running time.
So just a quick question about that. So what you were saying was like delta is like union of cycles, but what it boils down is like actually the step you have to take is just that delta is a single cycle.
A single cycle. In fact, the optimal is a single cycle.
Optimal is a single cycle. Okay. And is that why you said it's a combinatorial problem trying to?
So you've got like it's a much easier structure to deal with. You have these cycles in the graph, and we'll just route flow along a cycle and make progress. So you want to solve almost linear number of these problems. You don't have to solve them exactly. A crude approximation is good enough. And this is also very important because these paths and length problems on graphs, if you want a crude approximation, you can do with trees. You can do amazingly using trees. That's where we'll get our next wins. If you want to solve it exactly, we don't know how to do it very fast. But if you're willing to just approximate it, then we'll do it.
So trees.
I'm just coming to it next.
And what do you mean by a crude approximation?
So, for example, polylog is good enough, polylog approximation. But in fact, we'll go even worse to, like really subpolynomial, 2 to the root log n, let's say. Right, so really crude approximation, but you pay that in the running time now, and that's okay, right? We can afford to pay that. Okay, there are more interesting things. So these problems are not completely unrelated to each other. You get a sequence of them. And in fact, the gradients and the lengths, like if you look at all of these problems together, they don't change much. You only change coordinates of the gradient or the lengths, basically just linear number of times. So on average, you're only changing a constant number of coordinates from one problem to the next. Very few coordinate changes one problem to the next. Turns out this by itself, right? This is so now the problems are related. Maybe you can hope I can modify the solution and the work that I did on the first one to get a solution for the second one faster. This by itself also is not enough for us because just changing a few coordinates can dramatically change the structure of your optimal solution. Right. So but we can show something more, that in fact there exists a good hidden direction all throughout. So if you look at the current flow F and look at the direction to the optimal flow, to the unknown optimal flow, that direction gives you a good solution to each of these subproblems. Right? Just draw a straight line from where you are currently to the hidden optimal solution. That direction is good always for all of these linear number of subproblems. That's a good direction.
So good. Sorry.
Yeah. So good quantitatively for us means that it solves the mean ratio problem to a constant.
I see. So for every F, you're saying its direction to all of those are good.
Right. So not for every F. So F is the point you are currently at.
Oh, I see. So iteratively.
Right. Iteratively, wherever you are to the same hidden point, that makes progress. Right? This is a stronger relation between the solutions rather than just saying that the coordinates and lengths don't change. I'm saying that the structure of the solution is also not changing much.
You're saying you can find this?
Good. So we can solve these problems in small cumulative time, small amortized time. Questions about the IPM and this idea.
The approximate solution random in some sense, a random cycle.
Carefully chosen, but our solution is random. Like it's 60 pages of algorithms to make sure we solve these. 60 pages of data structure more carefully, but to solve them efficiently. But our solution is randomized. We don't know how to do it.
So this 4 is what gives you the bound on 1 using your approximate solution, or like
right? Good. So suppose you're getting a kappa approximate solution, then that means you are making progress that's like 0.1 over kappa. Then we'll do roughly kappa squared steps. Each of them will make progress 1 over kappa squared, and that'll be enough for us to get close to it.
I guess the bottleneck then is whatever the data structures you use to do 2 on it.
Yes. So now you have this sequence of problems that are changing slowly. I have a good optimal structure solution. Now we will build data structures to solve them efficiently. Right? Okay. So is the outer algorithm clear to us? Right. So what have we done? Rather than pick a faster IPM, we've gone to a slower IPM. But in the trade-off, we've gotten a problem that looks nicer and more combinatorial on graphs. We know the optimal solution is a cycle. We know these problems are changing slowly, and there is a good hidden direction for all of them. Okay, good. So that brings us to the second key ingredient in the algorithm is a data structure to solve all of these problems efficiently. Right, and this sort of forms our inner algorithm. Right, like so we have the outer algorithm as the L1 IPM, and this data structure is okay. So rather than dive in, let me first show you the next key idea as to why trees are a nice way to try to attack things. So let me show you something much simpler. I am giving you one subproblem. I want to just solve this subproblem approximately and in linear time. It's a much weaker goal, but let me show you how can we do this. So here's what we're going to do. The algorithm is simple. We'll sample a random low stretch spanning tree. If you don't know what a low stretch spanning tree is, don't worry. But it's some distribution on trees. Sample a tree from that. Given this tree, it's known how to do it in linear time. So that's the first, almost linear time. Given this tree, look at all the fundamental cycles in the tree. Right? You take a tree, you add an edge, you get a unique cycle. That's a fundamental cycle. You test the objective that this fundamental cycle achieves and return the best of it. Right? So you don't have to test all the cycles in the graph, just these M fundamental cycles because of the tree. And we'll show that this actually achieves a good approximation. Okay, so that's a proof that I'll present to you. So we'll denote fundamental cycle of an edge E with respect to the tree T as like a cycle TE. And this is not immediately obvious, but because all of these are with the same tree, you can test all of them in linear time. So this is a linear time, almost linear time.
Sorry, here is M is N. Like when you say tree, it's like you just said.
But there is an original underlying graph, right? The graph has M edges.
That's right.
And the off tree edges are N minus N, right?
Okay. Fair.
So, and you have to test all of them. Okay, so I'll try to show you this visually, right? And I want to prove to you that one of the fundamental cycles is a good approximation. And good is, in fact, a polylog approximation.
So, yeah, what's the property of the low stretch?
Let me write that here. So what is the property of a low stretch spanning tree? So here's, I'm just saying, let's say we sample a tree, blue is the tree edges. Here is the guarantee of a low stretch spanning tree. It says the following. So I'm in fact talking about the guarantee of the distribution, right? So this distribution over trees that we are sampling from guarantees the following. Fix any off-tree edge. Look at the length of the fundamental cycle of that off-tree edge. Over the distribution, average over the distribution, the expected is not much larger than the length of the edge.
So the distribution over the.
So there's the distribution over trees.
And N over the.
No, fix an edge. Worst case edge. Fix any edge. Sample a tree. In expectation, the fundamental cycle is not much larger measured by the length.
If the edge is in the tree, you just declare it to be 0.
One.
One.
Yeah, just let's say 1 or 2, like if you're looping it together. So yeah, the fundamental cycle, you make it 2, let's say.
So the low stretch is not property of the tree itself, but of the distribution.
Good. So you can change. This is a property of the distribution. You can make it. You can also ask for something that doesn't suffice for us. But if when literature says low stretch tree, It means averaged over the edges, the stretch is small, right? But the distribution property is in some sense stronger. It says, give me any edge. Over the sampling, you get an expectation small stretch. Right? Okay, so for every edge, this fundamental cycle is not much larger. That's the guarantee of the distribution. So let's do the following. Let's try to prove that you get a nice approximation. So let's pretend this is the hidden mean ratio cycle in green, sending 1 unit of flow all along the outer edges. I can now apply the guarantee of the low stretch distribution to say, let me sum over each of the mean ratio cycle edges, the guarantee, right? Like, so the guarantee was expected stretch of the expected length of the fundamental cycle is not much larger. Sum over your outer edges, sum over the edges in the mean ratio cycle. That means I can, with linearity, I can say that in expectation, the lengths of the fundamental cycles of all the edges in the mean ratio cycle is not much larger than the length of the mean ratio cycle, right? So this is many cycles now. Instead of one cycle, I've got a collection of fundamental cycles that's not much larger. Right? So the length is not much larger, but the gradient is in fact even easier, right? So, okay, so if the length is not much larger than expectation, we'll just apply Markov, say with higher probability half, you lose another constant factor. Probability half, you have a good sum of lengths of fundamental cycles. Good. Now look at the gradients. For each of the fundamental cycle, like these, the red arrows point the like it's a circulation along the fundamental cycles. All the tree edges cancel perfectly. You get a contribution, positive contribution in one cycle and a negative in the other. Right? So when I sum together these red circulations, the gradient contributions of the tree edges completely cancel. You're only left with your original cycle. So in fact, the sum of the gradient contributions of the fundamental cycles gives you back exactly the gradient contribution of your optimal cycle. Right? So looking at these union of cycles, the gradient contribution is the same. The length is not much larger. And you look at the ratio, so at least one of them, by averaging, at least one of them gives you a polylog approximation.
I have a question regarding this length thing. So you mentioned that in literature, like when they talk about this, what was the word, the stretch, low stretch.
A single low stretch band.
Right. They talk about like for average, like if you take the average, it should be like less than the thing or something. But here, you're not really using individual edges, right? It still looks like sum or average.
Yeah, but it's a sum over a hidden cycle.
Okay. Oh, it's not over.
It's a sum over a hidden unknown cycle. I don't know what edges I'm summing over. It's not a sum over all cycles. All edges.
I got it. Yeah, because here it was all edges because that was the entire.
Right.
It's not
right.
Okay.
But it's not. It could exclude many of the edges. But if this was sum over all edges in the tree, not in the tree, then you're right. Then we could just pick a low stretch.
In this case, it just happened to be.
Right. Visually, it was the easiest way.
That makes sense.
Right. Okay, so by averaging, you found a good cycle. Like one of the cycles is good. And now, of course, this was the probability half. You can boost the probability by sampling one of them. Right? Sample many trees. One of the fundamental cycles will be good with high probability. Right?
It's a little bit.
Yeah.
So how do you know? Seems you do it many times and you pick those lowest.
Yeah, just pick the lowest. I mean, in fact, the good thing is we actually even have a specific target, right? You know that it's good enough to get close to a constant. This is our bar. It's not a hidden value, right? We know it's close to a constant. So if you get 1 by polylog, amazing. Just take that.
Because I was worried if you pick a bad one.
Right. Yeah.
You just avoid it.
Right. So you can just, yeah, if you don't get it. Okay. So that sort of gives you an inspiration that if we can work with trees and we are willing to approximate the solutions, we can. Okay, good. That gets me to sort of, in some sense, the ideas that were easiest to convey. But let me state what is the theorem we prove from here. I have not given you the key ideas, but what is the theorem we are able to prove? So we are able to show a randomized data structure that maintains a collection of these trees. Okay, so it's not one tree; it's a collection. Not many, subpolynomial, right? But it's still a large collection of trees. That supports operations, efficient operations. What do these operations allow us? One, it allows you to update gradients and lengths. Okay, so remember, our low stretch trees depend on the length, right? Like our distribution has to change. If I change some length, I might have to resample some of the trees. So this distribution changes as the length changes. It allows us, our data structure allows you to change these lengths at a small cost per coordinate. It allows us to return an approximate mean ratio cycle in our setting, right? Like we need the assumption of a stable hidden direction, right? So this theorem is slightly informal. I'm not stating all the, like in our setting, it allows you to find an approximate mean ratio cycle at each iteration. And the third thing you have to support is once you identify a cycle, please route some flow along this, and then give me back the updated lengths and gradients.
So in other words, like pick the trees at somehow random in the beginning, and then you're always going to be taking the best with those.
And then we are going to keep updating them.
Updates are going to be
right.
Yeah.
So
somehow you want to guarantee that the updates still are good. Random.
Good. Yeah, good catch. So adaptivity. So right. So that's where it all, like many of these things start to get hairy now, right? Because this was Markov is a very difficult thing to de-randomize, right? Like you did it for one step. Now you updated gradients and lengths, but the choice of edges where you're updating it is not independent of the previous one. So your previous claims kind of you said that it's true. Even if you assume it was true, it may no longer be true because the choices are not independent. So this adaptivity is a big concern. I will not talk about it today, right? But it is an issue. It's hand level, let's say, right? Like, but before even going to adaptivity, let's pretend these changes were fixed beforehand. So the adversary doesn't see what updates you made before telling you what lengths and gradients to update. Still getting an efficient data structure is a difficult question. Right, and I'll just say maybe one more line since we're talking about adaptivity. If you know adaptive data structures, we will not end up doing a fully adaptive data structure. Oblivious is not enough for us, but we don't know how to do fully adaptive. But we'll get to a middle that suffices for these special collection of problems. Okay, so with these sort of at least high-level pictures of these two components, let me tell you what our algorithm looks like. The algorithm looks as follows. So you have a data structure that's maintaining a collection of a few trees. We'll go to linear number of iterations. At each iteration, you update the gradients and lengths. You update the trees according to these lengths. The trees return you a cycle that approximately minimize about some flow along this cycle. That's your update. Go back. This is roughly what it looks like. Okay. All right. So we're roughly. Yeah.
What was alpha there? I missed. What's this alpha?
You take some step along this cycle. You can't like.
And you have an upper bound in alpha because you
a lower bound in some sense, right? Like I want to move far enough, but not too far. Like there's a good medium that still gets you linear number of iterations. Yeah, I didn't specify how to pick it, but we can pick it specific. Okay, so let me try to give you some sense of what is involved in making a dynamic data structure. Right? Again, I will not be able to give you everything, but let me lead by questions and try to give you partial answers. Okay, so let's do this thought experiment. Right, we said you can sample spanning trees with half probability they're good. Let's say you've sampled many, so with polynomial probability there, with one, only like the failure probability is tiny. So here's one tree. Let's say this is really good. You identified a good circulation, you routed it. Now you got some length changes. Okay, so some of these, so remember, what was our fundamental cycle that I'll call an edge routing, that you took an off-tree edge, you connected it via the path in the graph. This is what, let's say, what you routed. So over a few iterations, you get length changes. And let's say some of these edges, these dashed blue edges, have their lengths change, their lengths become much longer. Increasing lengths of tree edges is a problem for us, right? Because that sort of destroys the average stretch property. If the tree edges become much longer. So now this tree may no longer be good. I've lost tree edges, they became much longer. And we don't have the time to recompute the entire tree, right? At least not every time. So what do? Can we salvage some of the tree? And the main idea is that, like, at least one idea is clear, right? If there's a routing that completely avoids these blue edges, those routings are good, right? If you had a green edge here, this routing is untouched. So if the tree was good beforehand, it's still good. But what about this green edge? I claim even for this green edge, you can pick a partial routing that's good. These, as long as you're not touching a dashed blue edge, so take the routing of the black edges, that's still good. They're like, the entire cycle is not good yet, but there's some partial routing which doesn't use these dashed blue edges, and that's good.
So what do you mean? You mean like a...
Yeah, so do I have I highlighted this? Yes, good. So the green part is still a good routing in the sense that the length of the entire green part is not much longer than the edge, assuming that was true before, right? You only cut parts of the cycle out. So what you could do is that, and that's true for every off-tree edge. Right, so now these are not full cycles, but you've chopped them because of these dashed blue edges that you've lost.
I'm just not sure what you're going to do now.
Okay, but is this part clear? The partial routing idea clear? Like that the entire cycle is not good, but as long as I'm not using the dashed blue edges, that part is good.
Sure.
Right? Okay, good. So let's get to. So these, we'll call these partial routings onto a forest, right? It's not a tree, you've thrown out some edges, but it's a partial routing onto a forest. The hope is that we can fix this tree more efficiently than resampling everything entire, right? That's the main. Okay, let me show you the key idea behind this. This is this is an idea called J trees or dynamic J trees from some of Madhuri's work. Not the Maxwell one, but you might have heard of it. If you haven't, let me show you the key idea. So here's...
So what is marked green here? Are
good.
these like...
Green are off-tree edges. I have not marked their partial routings. Black are tree edges. Dashed blue are tree edges that got too long, so we have to throw them out. So what partial routings are good? For example, for this one, you can take the green edge and go, as long as you are going only on black edges, that's good enough. Okay.
Sorry, I should just wait.
Okay, so yeah, so I'll just show you visually. So do the following. Look at connected components in this forest with just the black edges. Okay, so here's one component, one component, one component. So these 4 components, just contract them. You get to a smaller graph now. Right? So all the black edges disappeared. All the green edges become mostly across components. They can still be in a component, but then it doesn't matter. But you still have, like, I've not drawn the dashed blue edges, but you get this core graph by contracting. So it could be a much smaller graph. Right? If you've deleted k edges, this only has k plus 1 vertices. Right? So it's a much smaller graph. And now the main point is that you can find good routings on this core graph or a low stretch tree on this core graph, and then use that to patch the original. Use those as the crossing edges to patch the original tree.
What's a J tree? Sorry.
These are J trees. This notion is exactly J tree, that an edge that's not too long, any edge that's too long, like you sort of cut and you sort of make a shorter graph, like smaller graph. So you can ignore this, like we don't need to know. I was just drawing a reference to those who might be familiar. But this idea is sort of born from there. Going to a smaller graph, and that allows you to fix the original.
So you mean those little- So there's little.
It's actually not clear to me. The J was a parameter in the definition. It was, let me just, I would say more on video, let's say. Yeah, it was a parameter as to the scaling, like what is the ratio of the two layers.
Sorry, can you explain the
Yeah.
fix again? So you
Good.
go to the core graph.
So you got a much smaller graph, find a low stretch tree here,
Okay.
and then use those edges to patch to convert this forest into a tree. Right? The union of the black edges and the new smaller tree you will find will be a tree in the original graph.
Makes sense.
And you have to prove like it's high probability over I'm not sure what, you can find it.
Yes, like, yeah, lots of those. So ignore the probability, assume you had a good tree, it's still unclear.
I guess you want to show that it cannot happen that you have too many edges that stretch all
Yes.
the time.
That's right.
Sometimes it happens, but then we're guys.
That's right. So right. So that we get because on average the stretch is good. So only, yeah, you want to show that you can't have a lot of congestion. You can't have a lot of these using the same blue edge. So we have to add on this, right? So all of that has to be maintained. But the key idea is that you can reduce and work on a smaller problem to fix this, right? And the smaller problem is in some sense growing somewhat slowly, right? You get one more vertex every time I delete an edge at the upper layer. Okay, so let's visualize that change. So I already said this, how do you fix the original tree? You recurse on this smaller graph.
Isn't this graph like constant size most of the time?
No, we'll have like n to the 0.9. So it will be smaller, significantly smaller, but not a non-trivial.
Maybe in the beginning it's constant.
In the beginning it's constant, but very soon it will build up.
I thought that the average up at the average.
Right, so even if I change only one edge at a time, there are m iterations, right? So once I've made n to the 0.1 changes, it's an n to the 0.1 sized graph. It'll start going, but I've made n to the 0.9 changes, then it's a very large graph that I have to deal with. Right? Okay, so here's sort of the key idea that if our original forest was good, it preserved the low stretch. It preserved the hidden cycle, then in fact, after contraction also, you have a good mean ratio cycle. Right? Like if your original tree was good, even after contracting, you have a good mean ratio cycle in the smaller tree. Right? We need this. That's so we will end up finding a cycle in the smaller tree. Okay. And the other aspect of this is this core graph changes, right? You can ask, how does this change? So let's just observe what are the changes. So
Could you go back one?
Yeah,
What is the curse?
find a low stretch tree, a good low stretch tree on this, or sample a good low stretch tree on this code.
What's recursive about it?
It's we won't do one level, we'll do many levels.
Okay.
Right? Yeah. So let's so at the top level, it's an n size graph. Every time you get a change, you have this one smaller graph. The moment this becomes n to the 0.9, like very big, but not all the way, then you sort of rebuild the entire tree at the top level, and this will vanish. But within this span of n to the 0.9, we'll have another level n to the 0.8 here, because it's the same problem. You're trying to sample a low stretch spanning tree, and this is also getting changes. So we'll do another level. We'll do many, like something like root log n, log n levels of this size reduction.
So the core graph itself is like you have another core of.
We'll have again a core of the core graph, but yeah.
Big changes is like very small.
Yes. Right, so you get changes, you need to keep changing this, so it solves the same problem. Then we'll have another one that's capturing the changes in this problem, in this problem as well. Okay, so what kind of updates does this undergo? So one thing is easy-ish, that you do, like you can sort of. Let's observe. Okay, so what if, like, this is one iteration. You have your core graph, current core graph, current original graph. Now I delete one more edge, right? Like some tree edge undergoes a length update. Let's say it's this one, and you split into two components, right? That means I have to split a vertex in the core graph into two vertices and split their edges, right? So that's the operation. You're undergoing edge insertions, deletions, and this kind of vertex splits. This is somewhat of an issue. Why? Because, I mean, in my visual, these vertices don't have many edges. But remember, the core graph, it still has almost all the edges. It has few vertices, but it has almost all the edges. So the vertices can have very high degrees. So this vertex split operation, although it's actually not even compact to describe, because you have to describe which edges live on the first one and which of them move to the second one. So these are like the description length of these changes is actually not really large. Because if I have to summarize, this is an issue because you've done vertex reduction, but you've not done edge reduction. And you should be doing edge reduction also on top of the vertex. Right? So this core graph undergoes edge updates and vertex splits. Every edge updates, as I said, can lead to many things. Like a vertex split, like you could have linear number of edges moving from one to the other. So that's not good. And the fix is that you don't maintain the entire core graph, you maintain a sparse subset of the entire core graph, right? A cleverly chosen sparse subset, right? So we'll do edge reduction. So we'll build a sparsifier of this core graph, right? In fact, of every core graph. So it's always a recursive thing. So to build a sparsifier, so instead of all the green edges, we select. So remember, these are mostly off-tree edges we are talking about, right? Like of all the off-tree edges, we'll decide to keep only a small subset.
So
the blue edges.
So
yeah,
is it like the goal of this sparsifier should be like you still should get a decent low stretch span?
Yes, Good. So what are the properties of the sparsifier that will let us still fix the original tree without losing much? So the sparsifier has to be cleverly chosen. So let me tell you what are the properties. So we'll pick a sparse subgraph that preserves lengths up to a polylog factor. Right? Every green edge that you didn't pick can be routed using blue edges without much increase in length. Right? So whenever you wanted to use the green one, instead you use this blue route that's not much longer. Right? So and that means that if you had a good tree in the green, you will still have a good tree, or a good cycle in the green, you will still have a good cycle. Okay, so right, so not only do you want to know that there exists such a path, we'll maintain these paths explicitly because we'll need to query them, route flows along them. So you want to maintain this sparse subgraph along with explicit embeddings for each of the edges that will allow you to route these edges. Okay, now we need to argue, right, there's a good solution. Where does the good solution, right? So we are able to show the following. It's a pretty simple argument. That, so if the core graph, so G by F is the core graph, like you're contracting the forest, F is the forest. The core graph has a good cycle. Either so there's some fundamental spanner cycle is good. What is a fundamental spanner cycle? Take a green edge that's not in the spanner. So the spanner is a subgraph, the sparsifier. Take a green edge, look at its routing in the blue edges in the spanner, you put them together, you've got a cycle.
And we call it a spanner because of the length preservation property.
That's right. So that's like a spanner is a well-defined notion. Exactly, a spanner subgraph preserves these lengths. So, right. So either one of these fundamental cycles is good, or the spanner itself has a good cycle. We can prove this dichotomy. Right. So is the dichotomy clear? Either you find it in one of these edges that you're throwing out, right? One unique cycle for each of these edges that you're throwing out, or the sparse graph you're left with has a unique cycle. Right. And the funny thing is the proof is exactly the same as I showed you with the tree. You look at all of these cycles, the sum of their lengths is not much larger, and the sum of the gradients like cancels exactly to get you the original gradient. So one of those cycles works well. Okay, so now you had vertex reduction. This piece gives you edge reduction.
So how hard is it to do this sparse subgraph?
Yeah, so this is also new. This was not known to do this to main. Like it's also like spanners were known, but there are many things we need to provide, right? Like that to work under these vertex splittings, that to work on against an adaptive adversary, right? And they don't have to sort of blow up because you have to do them again and again recursively, right? Like they also don't have to cause many changes at the next level if I change something here. So that's our next piece in the data structure is that we give an algorithm to maintain a dynamic spanner. Some of these properties hopefully will make sense. So ignore the max degree condition, but technically we need a max degree condition to provide this. So you are given a graph that's going edge updates. You can insert edges, delete edges, or split vertices, right? Like that's what's happening to our core graph. You are getting edge updates and vertex splits. Under these operations, we can maintain a sparsifier, right? Or the spanner of the graph. What are the properties? One, every non-spanner edge has a good routing, not much long, right? Like that's the first property we wanted. You have it. Two, not only does there exist one, we can maintain it explicitly. Like for every non-spanner edge, maintain an explicit spanner path that's short. So also want the other way around. We want low congestion. We want no spanner edge is used in too many of these paths, right? because we are deleting edges, inserting edges, congestion is a problem for us, right? Like, so we want to make sure the congestion is not much more than what's necessary. So we can maintain that. Low congestion spanner, low length, like low stretch and low congestion. Both, we can get both of them. The other thing is this spanner doesn't change very frequently, right? You are deleting lots of edges, inserting edges. We don't want the spanner to suddenly change completely. In fact, the spanner changes very slowly, almost constant changes per update. So good running time, and it also works against adaptive, right? So even if like I make a change, you saw the change, and then you go back and tell me what is the next edge to delete, you're still good against an adaptive. Right? So we need to name this dynamic spanner piece. That's also.
So what's the size of the spanner?
Good. Thank you. I did not specify that. The size of the spanner is, if you're left with k vertices, it's k times 2 to the root log n. Right? Almost linear in the number of vertices that are left. Right. So now that's interesting, right? Because now if you got a reduction from n to n to the 0.9 vertices, I also reduce the edges to roughly n to the 0.9. Okay, so this theorem maybe was a bit too much, but let's step back. How does our data structure look like at a high level? So as I said, this was sort of recursive. So we're going to do this again. So at the top level, you have your original graph that's undergoing some length changes, some gradient changes. We sample a few let's say log n, those like we wanted with high probability, we want log n sample, log n low stretch. There were trees, but there's really sort of forest, right? Because you're deleting edges, so they're no longer trees. For each of these forests, you get a core graph, right? By contracting the components, you get these core graphs. To the core graphs, we want to apply our sparsifiers. So each of them, you pick a spanner. You get for each of the forests, you had a core graph. From the core graph, you got a spanner. At these spanners, we'll recurse. Right. So for each of these spanners, you again sample log n spanning trees, build their core graphs, build their spanners. And we'll do something like, let's say, log n levels of this. Right. So that's the entire data structure. But what is the guarantee? Right. So few guarantees. So at each level, the number of graphs is growing, log n to the I. So we can't sort of bound it. The depth has to be small, but the number of edges and the vertices are reducing, right? So the sizes of these graphs are reducing. So you can do more work more frequently at the bottom levels, right? You don't want to touch the upper graphs very frequently, but at the bottom level, you can keep resampling trees again and again. The guarantee is that if you take a fixed edge, there exists one path in this data structure that preserves the edge to a short length, right? So remember, what in the trees, what was the guarantee? One of the trees preserves the edge with high probability, right? So one sample preserved it with probability half. You sample log n and do a union bound. For every edge, you've got one of the trees, and that you sort of then take recursively. So there is one path down this tree. There is one path in this picture, and that path corresponds to a single spanning tree that preserves a fixed edge. So if you were to look at all cycles generated in this data structure, at least one of them will be good. So now these are not only tree cycles, right? Because we also got these spanner cycles. So either it's a tree cycle or a spanner cycle, or it's a tree cycle or a spanner cycle. And in this entire spread, you will find one of those cycles. Okay, I should leave it at that. So the key point is that we can maintain this expanding collection efficiently. Your running cost stays almost constant per update. Okay, so let's sort of start zooming back up. So in this tree chain, right, like we call this a tree chain, right? The branching tree chain. How do you find this cycle approximating? So you have a lot of these trees, log n to the d, but one of them gives you a good solution. Okay. And what are the candidates? Right? I said this one, but let me say this again. They are sort of these fundamental spanner cycles now.
What do you mean by pre-images? Sorry.
Right, good. Good catch. When you go to a core graph, in some sense, you're moving the edges, right? So if I found a spanner cycle at the second level, I have to move it back to the original graph, right? So those edges have to move back to the, like, what is the location of the original edges? So you found a cycle here, it has to correspond to a cycle at the top. That's what I mean. Okay. The good thing is, as these trees change slowly, you can explicitly check these fundamental cycles because you have these explicit embeddings. Right? You look at the explicit embedding. Every time some embedding changes, I'll just check. That's it. I don't have to check all of them all the time. Right? So every time an embedding path changes, we'll compute its quality, and if it's good, then you found a good solution. Okay, so I will not dive into more details, but the hidden issue is adaptivity. This data structure I described only works against oblivious adversaries. What are oblivious adversaries? That don't get to see your work when issuing the next update. If they get to see your work, then the next update, then your independence is lost. Your Markov is violated at the next iteration, right? So you have to handle it. We can't handle it in generality, but we can handle it for our special case of problems. But the key fact, which is not true in a general worst case instance of mean ratio cycle problems, but is true for us, is that there is the same hidden certificate that is true all throughout, right? And we know how this certificate changes, right? F star is hidden, but unknown. But if I'm updating F by a single cycle, then this hidden solution also is updated only on that single cycle, right? So only those edges change. Like the others stay, the others edges, the contribution of them to the mean ratio cycle stays unchanged. And you know how is the hidden certificate changing as you update this. That's the key fact we use to be able to do this. Okay, let me just drop that and end here. I'm happy to take questions.
Questions?
Yeah, happy to take any questions. So,
We already asked the time, so we can keep talking over lunch.
Can you say something about how hard it is to find this exact solution to the
mean ratio cycle problem?
Yeah.
So you can solve it exactly in roughly polynomial time, but one instance. No, polytime definitely. In fact, M poly, almost single. And it's interesting. So we came up, we did this, we'd written up the paper, posted it, and then we realized somebody, like two authors, 1982, it's sort of a paper lost to history, had actually identified that you can do Karmarkers and get an L1 IPM that still makes the same progress. So at least one idea had already, I didn't include a citation there, but it's on the paper. But they still didn't, like there's many more pieces that we needed, that approximate solution is enough. They were solving it exactly, and that they changed slowly, all of that. So we couldn't cite it as black box. But yeah, like it's interesting that not only was it done in 1982, some social media user on a Chinese Quora website basically said, "Oh, I think this paper actually did something like it's pretty interesting." We didn't even know who to credit, an anonymous user.
So, is there any chance of improving the little one terms?
Good. So right now, as I said, it's okay. So to be precise, 2 to the log n to the 7 by 8. Log n to the 7 by 8. Right. We sort of know that there are 3 bottlenecks that give you, each of them giving you from half, 3/4, 7 by 8. Right, like these factors usually come from balancing n to the d with 2 to the d with an n term, right? Like, and then 2 to the d with the t term. Sorry. Yeah. So we know 3 bottlenecks, and yeah, and we don't know, like, we think, like, we believe this should be all doable down to polylons. So, but we'll definitely need new ideas. Right. So one of the bottlenecks you can already see in what I showed you is this recursive depth structure. Right. Your trees are blowing up. The number of trees you're maintaining are blowing up. That restricts your depth, and this trade-off already gives you one sub-exponential term. Sorry?
Could it be linear?
Exactly linear? No, I don't think so. But I think finally you could get m polylog.
So is that exact? No? Yeah, not to be linear.
Lower bounds, yeah. No, I don't know. Yeah. Yeah, I'd be amazed if there's anything more than the lower bound. Because you can't even say you have to sort something on like this.
I think I'm not a fine grained person, but I think there's not even anything. Yeah, under.
Yeah.